Imagine holding a grain of sand between your fingers. Now imagine that this tiny speck contains more atoms than there are stars in the observable universe. But here's the interesting part. Those atoms themselves are mostly empty space, and within that emptiness lies a quantum realm where particles pop in and out of existence, where reality itself becomes uncertain. Today we're going to travel from the quantum foam beneath your fingertips to the very edge of everything we can observe, and maybe even beyond. If you're ready to expand your perspective of the universe, hit that subscribe button and give this video a like. Let's get started. Let's start our journey by zooming out from Earth, but not in the way you might expect. Instead of simply getting bigger, we're going to understand what each level of scale actually means for our existence and our understanding of reality itself. The European Space Agency's Gaia mission has been mapping the positions and movements of over 1 billion stars in our galaxy with unprecedented precision. This isn't just cosmic cartography, it's revealing how our solar system moves through space and how our galaxy itself is structured. When you look at the night sky, you're seeing our local neighborhood. The moon sits about 240,000 miles away, which seems far until you realize that if Earth were the size of a basketball, the moon would be a tennis ball about 23 feet away. This distance, which humans first crossed in 1969, represents one of our species' greatest achievements. But it's barely the first step in our cosmic journey. The scale jump to our sun is where things start getting truly mind-bending. At 93 million miles away, sunlight takes 8 minutes and 20 seconds to reach your eyes. This means you never see the sun as it is right now. You always see it as it was 8 minutes ago. When you watch a sunset, you're literally looking into the past. The sun itself is so massive that it contains 99.86% of all the mass in our solar system. If you could drive a car to the sun at highway speeds, the journey would take over 100 years without stopping. But here's where the Voyager missions give us perspective that no number can fully capture. Voyager 1, launched in 1977, is now over 14 billion miles from Earth in interstellar space. The radio signals it sends back take over 21 hours to reach us. Yet after traveling for nearly 5 decades, Voyager has barely scratched the edge of our sun's gravitational influence. The Oort cloud, a spherical shell of icy objects that surrounds our solar system, extends almost 2 light-years from the sun. Voyager won't reach its inner edge for another 300 years. This is when the concept of a light-year becomes essential to understanding cosmic scale. Light travels at 671 million miles per hour, and a light-year is the distance light covers in 1 year, nearly 6 trillion miles. Our nearest stellar neighbor, Proxima Centauri, lies 4.2 light-years away. If our solar system were the size of a quarter, Proxima Centauri would be another quarter about 10 miles away. The space between stars is mostly empty, filled only with scattered atoms, cosmic dust, and the occasional wandering comet or asteroid. The Hubble Space Telescope has spent over 3 decades showing us that this seemingly empty space between stars is actually teeming with activity. Stellar nurseries where new stars are born, planetary nebulae where dying stars shed their outer layers, and the intricate dance of binary star systems all play out across distances that challenge human comprehension. When Hubble captures an image of a star-forming region like the Eagle Nebula, it's showing us stellar birth happening across dozens of light-years, in clouds of gas and dust so vast that our entire solar system would be lost within them. As we zoom out further from our stellar neighborhood, we encounter one of the most profound shifts in cosmic perspective. Our Sun, along with its family of planets, orbits within a structure so vast and complex that early astronomers could barely comprehend it, the Milky Way galaxy. Picture this. Our galaxy contains between 200 and 400 billion stars, each potentially hosting its own system of worlds. The Spitzer Space Telescope and more recently the James Webb Space Telescope have revealed that planetary systems are incredibly common throughout our galaxy. Nearly every star you see in the night sky likely has planets orbiting it. This means our galaxy could contain over 1 trillion worlds. each with its own unique story of formation and evolution. But here's what really challenges our understanding of scale. Our solar system takes 225 million years to complete just one orbit around the galactic center. The last time we were in this position in our galactic orbit, dinosaurs ruled the Earth. Think about that for a moment. Every major extinction event, every evolutionary leap, every moment in human history has occurred during less than 1% of our galaxy's rotation. The Milky Way itself stretches roughly 100,000 light-years from edge to edge, but it's remarkably thin compared to its width, only about 1,000 light-years thick in most places. If our galaxy were the size of a pancake 3 feet across, it would be thinner than a sheet of paper. We're located about 26,000 light-years from the galactic center, roughly halfway between the core and the outer edge, in what astronomers call the galactic habitable zone. The Event Horizon Telescope made headlines when it captured the first image of a black hole, but that achievement represents something even more profound about cosmic scale. The black hole at the center of galaxy Messier 87 is 65 million light-years away and has a mass 6.5 billion times that of our Sun. The image we captured shows matter spiraling around an object so dense that space and time themselves become twisted beyond recognition. The bright ring of superheated gas we see in that image is larger than our entire solar system, yet it appears as just a glowing donut in space. Our own galaxy harbors a supermassive black hole called Sagittarius A star, which the Event Horizon Telescope also imaged in 2022. With a mass 4 million times that of our Sun, it sits at the galactic center, orchestrating the dance of billions of stars through its gravitational influence. The fact that we can image these cosmic monsters represents one of humanity's greatest technological achievements, requiring telescopes across the entire planet working together as a single instrument. But galaxies themselves are not isolated islands in space. The Hubble Space Telescope's deep field images revealed something extraordinary. Everywhere we look in the universe, no matter how small a patch of seemingly empty sky we examine, we find galaxies. Thousands of them. The deepest image ever captured, the Hubble Ultra Deep Field, shows over 10,000 galaxies in a region of sky smaller than the area covered by a grain of sand held at arm's length. Each of those distant galaxies contains billions or trillions of stars. Each star potentially hosts planets. Each planet represents a world with its own geological history, its own potential for harboring life. When you look at that image, you're seeing more worlds than our minds can truly comprehend, stretching across billions of years of cosmic history. The Milky Way belongs to what astronomers call the local group, a collection of over 80 galaxies bound together by gravity across a region about 10 million light-years across. Our nearest major galactic neighbor, Andromeda, lies 2.5 million light-years away and contains roughly 1 trillion stars. Despite the vast distance, Andromeda and the Milky Way are actually approaching each other at about 250,000 miles per hour. In roughly 4.5 billion years, they'll collide and merge into a single larger galaxy that astronomers have nicknamed Milkomeda. This galactic collision sounds catastrophic, but space is so vast that despite containing hundreds of billions of stars each, the chance of any two stars actually colliding during the merger is virtually zero. Instead, the galaxies will dance together, their spiral arms unwinding and reforming, their stars scattered into new orbits around a combined galactic center. Our Sun, if it still exists as a main sequence star, will likely be flung to a different region of the merged galaxy, giving future inhabitants of Earth, if any exist, an entirely different night sky. The Dark Energy Survey and the Euclid mission are revealing that galaxy groups like our local group are themselves organized into even larger structures. Galaxy clusters can contain thousands of individual galaxies, bound together by gravity across regions tens of millions of light-years across. The Coma cluster, one of the nearest major galaxy clusters, contains over 1,000 known galaxies and has a mass more than 10 trillion times that of our Sun. When we step back even further from galaxy clusters, we discover one of the most stunning revelations in modern cosmology. The universe has structure on scales so vast that they challenge our very conception of what big means. The Sloan Digital Sky Survey, which has mapped over 1 million galaxies, revealed that the distribution of matter in the universe resembles a cosmic web, with galaxies strung along filaments separated by enormous voids, almost completely empty of matter. These cosmic filaments stretch for hundreds of millions of light-years, connecting galaxy clusters like beads on an invisible string. The largest known structure, the Hercules Corona Borealis Great Wall, spans roughly 10 billion light-years across. To put this in perspective, this single structure is so large that light from one end takes 10 billion years to reach the other end. That's nearly 3/4 the age of the universe itself. When you consider that the observable universe is about 93 billion light-years across, this structure represents more than 10% of everything we can see. But here's where the story becomes even more mysterious. Everything we've discussed so far, every star, planet, galaxy, and cosmic structure, represents only about 5% of the universe's total content. The remaining 95% consists of two invisible components that we can detect only through their gravitational effects: dark matter and dark energy. Dark matter makes up roughly 27% of the universe, and while we can't see it directly, its gravitational influence shapes everything we observe. The beautiful spiral arms of galaxies like our Milky Way exist only because dark matter halos provide the gravitational scaffolding that holds them together. Without dark matter, galaxies would fly apart as they rotate. The Planck mission, which mapped the cosmic microwave background with extraordinary precision, confirmed that dark matter played a crucial role in forming the first structures in the early universe. Computer simulations like the Millennium simulation show us how dark matter forms the backbone of cosmic structure. In these models, dark matter creates a web-like network of filaments and nodes, and ordinary matter falls into these gravitational wells to form the galaxies we observe. The Dark Energy Survey has mapped this invisible architecture across billions of light-years, revealing how dark matter connects the largest structures in the cosmos. Even more mysterious is dark energy, which comprises about 68% of the universe and is causing the expansion of space itself to accelerate. The Nobel Prize-winning discovery of this accelerating expansion came from observations of distant supernovae, stellar explosions so bright they can be seen across billions of light-years. These cosmic lighthouses revealed that space itself is stretching faster and faster, carrying distant galaxies away from us at ever-increasing speeds. The implications of this discovery fundamentally changed our understanding of the universe's fate. Instead of expansion slowing down due to gravity, as scientists had assumed, dark energy is driving galaxies apart at an accelerating rate. The Hubble constant, which measures the rate of cosmic expansion, tells us that space is stretching such that galaxies appear to move away from us at about 70 kilometers per second for every megaparsec of distance. A megaparsec equals roughly 3.3 million light-years, so galaxies that are 330 million light-years away are receding at about 7,000 kilometers per second, or roughly 2% the speed of light. This brings us to one of the most profound concepts in cosmology, the observable universe. When we look into space, we're simultaneously looking back in time. The light from distant galaxies has been traveling for billions of years to reach us, so we see them as they were in the distant past. The most distant galaxies ever observed, captured by the James Webb Space Telescope, appear as they were over 13 billion years ago, when the universe was less than a billion years old. The edge of our observable universe represents the cosmic microwave background, the afterglow of the Big Bang itself. This radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, fills all of space and represents the oldest light in the universe. When we observe this radiation, we're seeing the universe as it was roughly 380,000 years after the Big Bang, when it first became transparent to light. The Wilkinson Microwave Anisotropy Probe and later the Planck mission mapped this cosmic microwave background with extraordinary detail, revealing tiny temperature variations that represent the seeds of all cosmic structure. These fluctuations, smaller than 1 part in 100,000, eventually grew into the galaxies, stars, and planets we see today. In essence, the cosmic microwave background is a baby picture of the universe, showing us the initial conditions that led to everything we observe. But here's what's truly mind-bending about cosmic scale. The observable universe, vast as it is, might represent only a tiny fraction of the total universe. If cosmic inflation theory is correct, and there's strong evidence supporting it, the actual universe could be vastly larger than what we can observe. Some models suggest the total universe could be trillions or even infinitely larger than our observable bubble. The concept of cosmic inflation, proposed by Alan Guth and refined by many others, suggests that in the first fraction of a second after the Big Bang, space itself expanded faster than light, stretching a region smaller than a proton to a size larger than a grapefruit in an impossibly brief instant. This inflation explains why the cosmic microwave background appears so uniform across the sky and why space appears flat on the largest scales. Recent observations from the James Webb Space Telescope are adding new pieces to this cosmic puzzle. JWST has observed galaxies that formed when the universe was only a few 100 million years old, revealing that galaxy formation began earlier and proceeded more rapidly than many theoretical models predicted. These ancient galaxies appear surprisingly massive and mature for their age, suggesting that the early universe was a more active and dynamic place than we previously understood. The telescope has also peered into the atmospheres of exoplanets, revealing the chemical compositions of worlds orbiting distant stars. This capability connects the vast scales of the universe to the possibility of life itself. As we map the cosmic web and understand how matter flows along its filaments, we're also discovering that the building blocks of life, elements forged in the hearts of dying stars, are distributed throughout the cosmos. The question that haunts every astronomer who contemplates these cosmic scales is, how do we actually measure distances so vast that our everyday experience provides no reference point? The answer reveals one of science's most elegant achievements: a cosmic distance ladder that reaches from our backyard to the edge of the observable universe. The foundation of this ladder begins surprisingly close to home. Astronomers use a technique called parallax, the same principle that makes your finger appear to shift position when you close one eye, then the other. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. The European Space Agency's Gaia mission has measured these tiny shifts for over 1 billion stars with extraordinary precision, creating the most accurate three-dimensional map of our galactic neighborhood ever assembled. For stars beyond parallax range, astronomers rely on standard candles, objects whose true brightness we understand well enough to determine distance from their apparent brightness. Cepheid variable stars, discovered by Henrietta Swan Leavitt in the early 1900s, pulsate with periods directly related to their intrinsic luminosity. The longer the pulsation period, the brighter the star. Edwin Hubble used Cepheids in the Andromeda Galaxy to prove that it lay far beyond our own galaxy, fundamentally expanding our conception of the universe's size. For the most distant reaches of space, astronomers rely on Type Ia supernovae, stellar explosions so standardized and bright that they can be seen across billions of light-years. These cosmic beacons all reach nearly the same peak brightness when they explode, making them perfect rulers for measuring the expansion of the universe itself. The Supernova Cosmology Project and the High-Z Supernova Search Team used these stellar explosions to discover that cosmic expansion is accelerating, a finding that revolutionized our understanding of the universe's ultimate fate. But measuring these vast distances required technological achievements that push the boundaries of human ingenuity. The Hubble Space Telescope, operating beyond Earth's atmosphere for over 3 decades, can detect objects billions of times fainter than what the human eye can see. Its successor, the James Webb Space Telescope, with a mirror area nearly 7 times larger than Hubble's, can observe galaxies so distant that their light has been traveling for over 13 billion years to reach us. The engineering behind these observations is staggering. JWST operates at a temperature of -370 degrees Fahrenheit, colder than the surface of Pluto, maintained by a tennis court-sized sunshield that blocks the sun's heat. The telescope's instruments are so sensitive that they could detect the heat signature of a bee on the moon. This extraordinary sensitivity allows us to peer deeper into space and further back in time than ever before possible. When we observe these most distant galaxies, we're seeing the universe as it was when it looked fundamentally different from today. The early universe was smaller, denser, and hotter. The cosmic microwave background shows us that roughly 380,000 years after the Big Bang, the universe had cooled enough for the first atoms to form. Before this epoch of recombination, space was filled with a hot, opaque plasma that scattered light in all directions. The period that followed, called the Cosmic Dark Ages, lasted for several 100 million years. During this time, no stars yet existed to illuminate the cosmos. The universe was truly dark, filled only with hydrogen and helium gas, slowly collapsing under its own gravity to form the first proto-galactic structures. The James Webb Space Telescope is designed to peer into this era, searching for the first stars and galaxies that ended the cosmic dark ages and began the process of reionization. These first stars were likely massive monsters, perhaps 100 or even 200 times the mass of our Sun. Unlike stars today, they contained almost no heavy elements because only hydrogen, helium, and trace amounts of lithium existed in the early universe. These population 3 stars, as astronomers call them, lived fast and died violently, exploding as supernovae that scattered the first heavy elements throughout space. Every carbon atom in your body, every oxygen atom you breathe, was forged in the nuclear furnaces of these ancient stellar giants. The concept of cosmic evolution reveals another layer of scale that connects the largest structures to the most intimate aspects of our existence. The elements that make life possible were created in stellar cores through nuclear fusion, dispersed by stellar winds and supernova explosions, and incorporated into new generations of stars and planets. This process, called stellar nucleosynthesis, links the life cycle of individual atoms to the grand story of cosmic structure formation. Carl Sagan famously said we are made of star stuff, but the full implications of this statement become clear only when we understand cosmic scale. The iron in your blood was forged in the core of a massive star that exploded billions of years ago. The calcium in your bones was created in a stellar furnace and scattered across space by a supernova shockwave. The gold in any jewelry you might wear was likely created in the collision of 2 neutron stars, an event so violent that it generated gravitational waves detectable by the Laser Interferometer Gravitational Wave Observatory. LIGO's detection of gravitational waves in 2015 opened an entirely new window onto the universe, allowing us to observe cosmic events that produce no light whatsoever. When 2 black holes merge, they create ripples in space-time itself that propagate outward at the speed of light. These waves are so subtle that they stretch and compress space by amounts smaller than 1/10,000th the width of a proton, yet LIGO can detect them across distances of millions of light-years. The merger events that LIGO observes reveal another aspect of cosmic scale, the incredible energies involved in the most violent phenomena in the universe. When 2 30 solar mass black holes merge, they convert about 3 solar masses worth of material into pure gravitational wave energy in just a few seconds. That's more energy than all the stars in the observable universe produce, combined during the same time period. These discoveries connect the largest scales of the universe to fundamental physics in ways that continue to surprise scientists. The cosmic web of dark matter that shapes galaxy formation operates according to the same gravitational laws that govern falling apples and orbiting planets. The expansion of space itself follows equations first written down by Einstein over a century ago. The quantum fluctuations that generated the initial density variations in the cosmic microwave background operate according to principles that also govern the behavior of subatomic particles in laboratory experiments. This deep connection between the cosmic and the quantum reveals one of the most profound insights of modern science. The universe operates as a unified whole, where the same physical laws apply from the smallest subatomic scales to the largest cosmic structures. The elegant mathematical descriptions that explain how galaxies cluster and evolve also predict the behavior of particles in accelerators. The theories that describe black hole formation also illuminate the nuclear processes that power stars. Understanding cosmic scale has practical implications that extend far beyond pure scientific curiosity. The global positioning system that guides your navigation depends on Einstein's theories of relativity, which were developed partly to understand cosmic phenomena. The technologies that enable modern astronomy, from CCD cameras to computer modeling, have found applications in medical imaging, weather forecasting, and countless other fields that benefit humanity. Now we arrive at perhaps the most mind-bending aspect of cosmic scale, the realization that the universe might extend infinitely inward as well as outward. While we've been journeying toward the largest structures in the cosmos, an equally profound exploration awaits us in the opposite direction, toward the quantum realm, where reality itself becomes fundamentally uncertain, and where the very concept of scale breaks down in ways that challenge our understanding of existence. The scale jump from human-sized objects to quantum particles is even more dramatic than the leap from Earth to the observable universe. If you could shrink down to the size of an atomic nucleus, you would find yourself in a realm where the classical physics that governs planetary orbits and galaxy rotations simply no longer applies. Instead, you'd encounter a strange world where particles can exist in multiple states simultaneously, where the act of observation changes reality, and where empty space itself seethes with virtual particles popping into and out of existence. The Planck scale, named after physicist Max Planck, represents the smallest meaningful unit of length in our universe, approximately 1.6 times 10 to the minus 35 meters. At this scale, the smooth fabric of space-time that Einstein described becomes a roiling foam of quantum fluctuations. String theory, one of the leading candidates for a theory of quantum gravity, suggests that at this scale, the fundamental constituents of matter are not point particles, but tiny vibrating strings, perhaps existing in additional dimensions beyond the three spatial dimensions we experience. What's remarkable is that these quantum fluctuations at the Planck scale appear to be connected to the largest structures we observe in the universe. The cosmic inflation theory suggests that quantum uncertainties in the early universe were stretched by exponential expansion to create the density variations we see in the cosmic microwave background. In other words, the vast galaxy clusters and cosmic voids that span hundreds of millions of light-years originated from quantum fluctuations smaller than subatomic particles. This connection between the quantum and cosmic scales reveals one of the most profound insights of modern physics. Scale is not just about size, but about the fundamental nature of reality itself. The Large Hadron Collider, humanity's most powerful particle accelerator, recreates conditions that existed in the first fractions of a second after the Big Bang. By colliding protons at energies of 13.6 trillion electron volts, physicists probe the fundamental building blocks of matter and energy that shaped the early universe. The discovery of the Higgs boson in 2012 at the LHC revealed how particles acquire mass through their interaction with an energy field that permeates all of space. This Higgs field, invisible and intangible, gives substance to the matter that eventually formed stars, planets, and life itself. Without the Higgs mechanism, electrons would be massless and atoms could not exist. The entire cosmic story, from the first stars to your own existence, depends on quantum field interactions that operate at the smallest possible scales. But perhaps the most profound implication of understanding cosmic scale is the possibility that our observable universe represents just one bubble in an infinite multiverse. Eternal inflation theory, supported by physicists like Alan Guth and Andre Linde, suggests that the Big Bang that created our universe was not a unique event, but one of countless expansions happening continuously throughout a larger metaverse. In this picture, what we call the universe might be just one region where inflation ended, allowing matter and energy to condense into the structures we observe. Beyond our cosmic horizon, infinite other regions could be undergoing their own Big Bangs, each potentially with different physical laws, different fundamental constants, and different possible histories. Some might contain universes where gravity is stronger or weaker, where electrons have different masses, or where the nuclear forces operate differently. The implications of this multiverse concept challenge our understanding of what makes our universe special. The fine-tuning that allows stars to form, planets to exist, and life to emerge might not be evidence of design, but simply the result of selection bias. We observe this particular universe because it's the one where observers like us can exist. In the vast majority of other possible universes, the physical constants might be incompatible with the formation of stable matter or complex structures. Recent observations from the James Webb Space Telescope are providing new insights into how our universe evolved from its earliest moments. By observing galaxies that formed when the universe was only 300 to 400 million years old, JWST is revealing that the process of cosmic structure formation began earlier and proceeded more rapidly than many theoretical models predicted. These ancient galaxies appear surprisingly large and mature, suggesting that the universe may have been more efficient at creating complex structures than we previously understood. The telescope's infrared capabilities allow it to see through cosmic dust that obscures optical observations, revealing star formation regions and galactic cores that were previously hidden. In the constellation Carina, JWST has captured images of stellar nurseries where new stars are being born at this very moment, their formation triggered by shock waves from nearby supernovae. These stellar birth announcements represent the continuation of a process that has been ongoing for over 13 billion years, connecting the early universe to the cosmic present. Understanding cosmic scale also reveals the temporal dimension of our cosmic journey. When you look at the Andromeda Galaxy, visible to the naked eye on a dark night, you're seeing light that left those distant stars 2.5 million years ago, when early human ancestors were just beginning to use stone tools. The light reaching your eyes from the most distant galaxies JWST can observe began its journey when the universe was less than 5% of its current age. This means that astronomy is fundamentally an exercise in archaeology. Every observation is a glimpse into the past, and the deeper we look into space, the further back in time we see. The cosmic microwave background radiation that fills all of space carries information about the universe when it was only 380,000 years old, a cosmic fossil that preserves the conditions of the primordial universe in exquisite detail. The Atacama Cosmology Telescope and the South Pole Telescope are mapping this ancient radiation with ever-increasing precision, searching for subtle polarization patterns that could reveal direct evidence of cosmic inflation. If detected, these primordial gravitational waves would provide our first glimpse of the universe during its first tiny fraction of a second, when quantum effects dominated over all other forces. But cosmic scale isn't just about distance and time, it's about energy and information as well. The total energy content of the observable universe, including dark matter and dark energy, is estimated to be equivalent to about 10 to the 69th joules. To put this in perspective, that's roughly the energy output of 1 billion trillion stars like our Sun operating for the entire current age of the universe. Yet, according to some interpretations of quantum mechanics, this enormous energy content might sum to exactly zero when gravitational potential energy is properly accounted for. This suggests that the universe might be the ultimate free lunch, arising from quantum fluctuations in a pre-existing vacuum state. The energy needed to create all the matter and radiation we observe could be perfectly balanced by the negative gravitational binding energy of cosmic structures. In other words, the entire universe might represent a quantum fluctuation that hasn't yet decayed back to nothingness. The information content of the observable universe provides another perspective on cosmic scale. Jacob Bekenstein and Stephen Hawking showed that the information storage capacity of any region of space is limited by its surface area rather than its volume, a principle known as the holographic bound. According to this principle, all the information contained within the observable universe could theoretically be encoded on its two-dimensional boundary, much like a hologram stores three-dimensional information on a flat surface. This holographic principle suggests that reality itself might have a fundamentally different structure than our everyday experience suggests. What we perceive as three-dimensional space might emerge from information processing on a lower dimensional boundary, making the entire universe a kind of holographic projection. The implications of this idea are still being explored, but they suggest that our understanding of space, time, and reality itself may need fundamental revision. As we contemplate these mind-bending scales, from quantum foam to cosmic horizons, we encounter one of the most profound questions in science. Are we alone in this vast universe, or does life exist elsewhere among the countless worlds scattered across cosmic time and space? The search for life beyond Earth takes on entirely new dimensions when viewed through the lens of cosmic scale, revealing possibilities and challenges that stretch our imagination to its limits. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy. When we plug in current estimates for star formation rates, the fraction of stars with planets, and the likelihood of life developing, the numbers become staggering. Even conservative estimates suggest that our galaxy alone could harbor thousands or even millions of intelligent civilizations. Yet despite decades of searching with increasingly sophisticated technology, we have found no confirmed evidence of extraterrestrial intelligence. This apparent contradiction, known as the Fermi paradox, becomes even more puzzling when we consider cosmic scale. The Milky Way is over 13 billion years old, and Earth-like planets could have formed billions of years before our own world came into existence. If intelligence arises naturally from the laws of physics and chemistry, some civilizations could be billions of years more advanced than we are. The question that haunts astronomers is, where is everybody? Recent discoveries by the Kepler Space Telescope and the Transiting Exoplanet Survey satellite have revolutionized our understanding of planetary abundance. We now know that rocky planets orbiting in their star's habitable zone, where liquid water could exist, are incredibly common throughout the galaxy. The TRAPPIST-1 system, just 39 light-years from Earth, contains 7 Earth-sized worlds, 3 of which orbit in the habitable zone. The K2-18b exoplanet shows evidence of water vapor in its atmosphere, suggesting that oceanic worlds might be abundant throughout the cosmos. But the scale of the galaxy itself might provide part of the answer to the Fermi paradox. Even if our galaxy teems with intelligent life, the vast distances between star systems create natural isolation. A radio signal from the nearest potentially habitable exoplanet would take over 4 years to reach Earth, and that assumes the signal is powerful enough to detect across interstellar distances. The inverse square law means that radio signals become incredibly faint as they spread across space, making communication between civilizations extraordinarily challenging. The search for extraterrestrial intelligence, conducted by organizations like the SETI Institute, has been scanning the skies for artificial signals for over 60 years. The Allen Telescope Array and the Green Bank Telescope have listened to millions of stars across a wide range of radio frequencies, searching for the technological signatures of advanced civilizations. The Breakthrough Listen project, funded by entrepreneur Yuri Milner, represents the most comprehensive search ever undertaken, monitoring over 1 million nearby stars for signs of artificial transmissions. Yet the challenge of detecting extraterrestrial intelligence becomes clear when we consider the scale of the search space. Radio waves travel at the speed of light, but even at this cosmic speed limit, signals from distant civilizations might take thousands, millions, or even billions of years to reach us. By the time we receive a message from a distant star system, the civilization that sent it might have evolved beyond recognition or ceased to exist entirely. The concept of technological signatures extends beyond radio communications to include other evidence of advanced civilizations. The James Webb Space Telescope is capable of analyzing the atmospheric compositions of exoplanets, searching for industrial pollutants, excessive heat signatures, or other signs of technological activity. If an advanced civilization has modified their planet's atmosphere through technology, we might be able to detect these changes from thousands of light years away. Some scientists have proposed searching for evidence of megascale engineering projects that advanced civilizations might construct. Freeman Dyson suggested that sufficiently advanced civilizations might build enormous structures around their stars to capture stellar energy, creating detectable signatures in infrared light. The Kepler mission has searched for the periodic dimming patterns that such structures might create, though no confirmed examples have been found. The scale of such projects would be almost incomprehensible by human standards. A complete Dyson sphere around a star like our Sun would require dismantling hundreds of Earth-sized planets to provide enough material. The construction would take thousands of years, even with advanced robotics and self-replicating machinery. Yet for a civilization with access to the energy output of an entire star, such projects might be as routine as building cities is for us today. The possibility of ancient alien artifacts within our own solar system provides another perspective on the intersection of cosmic scale and the search for life. If advanced civilizations have existed in our galaxy for billions of years, they might have sent robotic probes to investigate promising star systems like ours. These artifacts could be incredibly ancient, predating the formation of Earth itself, and might lie dormant on airless moons or in the asteroid belt, waiting to be discovered. The concept of panspermia suggests that life itself might travel between star systems, either naturally through the ejection of material during asteroid impacts or deliberately through the actions of intelligent civilizations. Microorganisms can survive the harsh conditions of space for extended periods, and some extremophiles on Earth thrive in environments similar to those found on Mars or the moons of Jupiter and Saturn. Recent discoveries about extremophiles have expanded our understanding of where life might exist in the universe. Organisms have been found thriving in the deepest ocean trenches, in highly radioactive environments, in extreme heat and cold, and in highly acidic or alkaline conditions. These findings suggest that life might be far more adaptable and widespread than previously thought, potentially existing in environments throughout the galaxy that we once considered completely hostile to biological activity. The moons of the outer solar system have emerged as prime targets in the search for life beyond Earth. Europa, one of Jupiter's largest moons, harbors a subsurface ocean containing more water than all of Earth's oceans combined. Enceladus, a moon of Saturn, spouts geysers of water vapor from its south polar region, suggesting an active subsurface ocean heated by tidal forces. These hidden oceans might have existed for billions of years, providing stable environments where life could potentially evolve and thrive. The upcoming Europa Clipper mission and the proposed Enceladus Life Finder will search these alien oceans for signs of biological activity. The instruments aboard these spacecraft will be capable of detecting organic molecules, measuring the salinity and chemistry of the subsurface oceans, and searching for the metabolic byproducts that living organisms might produce. If life exists in these hidden seas, we might discover it within the next decade or two. But perhaps the most profound implication of cosmic scale for the search for life is the realization that intelligence itself might be a cosmic phenomenon. The elements that make life possible, carbon, oxygen, nitrogen, phosphorus, were forged in the nuclear furnaces of ancient stars and dispersed throughout the galaxy by supernova explosions. The The same stellar processes that created the building blocks of life have been operating throughout the cosmos for billions of years. If intelligence represents a natural outcome of cosmic evolution, then the universe might be filled with minds contemplating questions similar to our own. Somewhere among the hundreds of billions of galaxies in the observable universe, other beings might be wondering about their place in the cosmic story, searching their skies for signs of other civilizations and marveling at the scale of the universe they inhabit. The possibility of multiple genesis events where life arises independently in different locations throughout the cosmos suggests that the universe might contain not just one tree of life but entire forests of biological diversity. Each independently evolved biosphere would represent a unique experiment in what life can become when given billions of years to evolve under different planetary conditions. This cosmic perspective on life and intelligence transforms our understanding of what it means to be human. We are not separate from the universe, but integral participants in its ongoing evolution. The carbon atoms in our DNA, the iron in our blood, the calcium in our bones, all have cosmic origins. We are quite literally made of star stuff, temporary arrangements of stellar debris that have achieved consciousness and begun to contemplate the cosmos from which we emerged. Understanding cosmic scale forces us to confront one of the most humbling and awe-inspiring questions humans have ever asked. What is the ultimate fate of everything we observe? From the smallest quantum particles to the largest cosmic structures, the story of the universe's future unfolds across timescales so vast that they dwarf even the 13.8 billion years that have already passed since the Big Bang. The discovery that dark energy is causing cosmic expansion to accelerate fundamentally changed our understanding of the universe's destiny. Unlike earlier models that predicted either a big crunch, where gravity eventually pulls everything back together, or a gradual slowdown of expansion, we now know that galaxies will continue moving apart at ever-increasing speeds. The Type Ia supernova observations that revealed this acceleration show us a universe rushing toward a cold, dark, and empty future. But the timescales involved in this cosmic evolution stretch our comprehension beyond breaking point. Stellar evolution models tell us that our Sun will continue burning hydrogen in its core for approximately another 5 billion years before beginning its transformation into a red giant star. When this happens, the Sun will expand to perhaps 100 times its current size, potentially engulfing Mercury, Venus, and possibly Earth itself. Yet this momentous event represents less than 1% of the time that will pass before the universe undergoes truly fundamental changes. The stelliferous era, the current age of star formation and stellar burning, will continue for approximately 100 trillion years. During this time, the universe will gradually use up its supply of hydrogen fuel, and star formation will slow and eventually cease entirely. The most massive stars will have long since exploded as supernovae or collapsed into black holes, while smaller stars like red dwarfs will continue burning their fuel with such efficiency that they could shine for trillions of years. As star formation winds down and existing stars exhaust their nuclear fuel, the universe will enter what cosmologists call the degenerate era, dominated by white dwarf stars, neutron stars, and black holes. Even during this incredibly distant future, spanning from 100 trillion to 1 undecillion years after the Big Bang, fascinating processes will continue to operate. White dwarf stars will slowly cool and fade. Brown dwarf stars will occasionally flare up as they capture stray material, and rare collisions between stellar remnants will briefly light up the cosmic darkness. The concept of proton decay, predicted by some theories of particle physics but not yet observed, could fundamentally alter the universe's evolution on these timescales. If protons, the building blocks of atomic nuclei, eventually decay with a half-life of 10 to the 34th years or longer, then all ordinary matter will gradually disappear. Planets, asteroids, and the corpses of dead stars would slowly evaporate into space as their constituent atoms disintegrate into lighter particles and energy. Even if protons prove to be completely stable, Quantum tunneling effects operating over unimaginably long timescales could cause dramatic changes in the structure of matter itself. The quantum mechanical probability that electrons might tunnel closer to atomic nuclei, or that entire atoms might spontaneously rearrange themselves into different configurations, becomes significant only when considered across periods spanning 10 to the hundreds or thousands of years. Black holes, which form when massive stars collapse under their own gravity, will eventually dominate the far future universe. Stephen Hawking's theoretical work showed that black holes slowly evaporate through a process called Hawking radiation, emitting particles and gradually losing mass over time. The rate of this evaporation is inversely related to the black hole's mass, meaning that stellar mass black holes will take approximately 10 to the 67th years to completely evaporate. The supermassive black holes that anchor the centers of galaxies, with masses millions or billions of times that of our Sun, will persist much longer. The black hole at the center of the Milky Way, Sagittarius A star, will require approximately 10 to the 87th years to evaporate completely through Hawking radiation. During the final moments of a black hole's existence, it releases its remaining mass energy in a brief but incredibly violent explosion that briefly outshines entire galaxy clusters. The heat-death scenario, first proposed in the 19th century and refined by modern cosmology, describes the universe's ultimate fate as a state of maximum entropy where all energy has been converted to heat and distributed evenly throughout space. In this far future, approximately 10 to the 100 years after the Big Bang, the universe will have reached thermal equilibrium at a temperature just barely above absolute zero. Yet even this apparently final state might not represent the end of cosmic evolution. Quantum fluctuations, the same random variations in energy that may have seeded the formation of galaxies in the early universe, continue to operate even in empty space. Over timescales of 10 to the 56 years, these fluctuations could theoretically create random assemblages of matter, including brief reconstructions of complex structures or even living beings. The possibility of vacuum decay represents perhaps the most dramatic potential future for our universe. If the Higgs field that gives particles their mass exists in a false vacuum state, as some theoretical models suggest, it could spontaneously tunnel to a lower energy configuration. This transition would propagate outward at the speed of light in an expanding bubble, fundamentally altering the laws of physics and potentially destroying all existing matter and energy in its wake. But perhaps the most remarkable aspect of contemplating these cosmic timescales is how they illuminate the extraordinary improbability and preciousness of our current moment in cosmic history. We exist during a brief window when stars are actively forming, when planets can maintain stable orbits around long-lived stellar furnaces, and when complex chemistry is possible in the narrow temperature range between the heat of stellar cores and the cold of empty space. The anthropic principle suggests that we observe the universe during this particular epoch precisely because it's the only time when observers like us could exist. The fine-tuning of physical constants that allows atoms to form, stars to shine stably for billions of years, and complex molecules to assemble into living systems represents a cosmic coincidence of extraordinary precision. Change the strength of the electromagnetic force by just a few percent, alter the mass of electrons by a small fraction, or modify the rate of cosmic expansion slightly, and the universe would be incapable of producing stars, planets, or life. Recent observations from the James Webb Space Telescope are providing new insights into how quickly complexity can emerge in the universe. Galaxies that formed when the universe was only 400 million years old already show signs of heavy element enrichment, suggesting that the first generations of stars lived and died much more rapidly than previously thought. This accelerated chemical evolution means that the building blocks necessary for planet formation and potentially life were available much earlier in cosmic history than many models predicted. The discovery of organic molecules in the atmospheres of exoplanets, detected through transit spectroscopy as starlight filters through planetary atmospheres, reveals that complex chemistry is indeed common throughout the cosmos. Water vapor, carbon dioxide, and methane have been detected in the atmospheres of worlds hundreds of light years away, confirming that the chemical processes necessary for life operate throughout the galaxy. Understanding cosmic scale also provides perspective on humanity's potential future as a spacefaring civilization. The enormous energies available in stellar fusion, the vast resources present in asteroid belts and comet clouds, and the possibility of terraforming or constructing artificial habitats suggest that intelligent life might persist and thrive even as individual stars exhaust their fuel supplies. The concept of galactic-scale engineering projects, while speculative, illustrates how advanced civilizations might interact with cosmic evolution itself. Moving entire star systems to avoid galactic collisions, harvesting energy from black holes through the Penrose process, or even attempting to influence the large-scale structure of space-time represent the kinds of projects that civilizations with access to stellar-scale energy sources might undertake. But perhaps most importantly, contemplating the future evolution of the universe on cosmic scales reveals the profound responsibility that comes with consciousness itself. In a universe trending toward maximum entropy and heat death, the emergence of intelligence represents a temporary reversal of this trend toward disorder. Living systems, and especially intelligent ones, create local islands of complexity and organization in a cosmos that is generally becoming more random and uniform over time. The scientific process itself exemplifies this principle. Every measurement we make, every theory we construct, every discovery we achieve represents the transformation of cosmic chaos into organized knowledge. The instruments we've built to explore the universe, from ground-based telescopes to space-based observatories, concentrate diffuse stellar radiation into focused information about the nature of reality itself. Your act of learning about cosmic scale participates in this grand project of consciousness, organizing, and understanding the universe. The neurons in your brain that process this information about galaxies and quasars, dark matter and dark energy, represent some of the most complex structures known to exist anywhere in the cosmos. In contemplating the universe, you become part of the universe's own attempt to understand itself. This recursive relationship between mind and cosmos suggests that consciousness might play a more fundamental role in cosmic evolution than we currently understand. Some interpretations of quantum mechanics propose that observation itself influences the behavior of physical systems, implying that the emergence of observers throughout the universe might affect its ultimate development and fate. The instruments and technologies we have developed to probe cosmic scale represent some of humanity's greatest intellectual and engineering achievements, each breakthrough revealing new layers of cosmic complexity that previous generations could never have imagined. The story of how we came to understand the true scale of the universe is itself a testament to the power of human curiosity and ingenuity operating across centuries of scientific discovery. Consider the revolutionary impact of the charge-coupled device, or CCD, invented in 1969 at Bell Labs for entirely different purposes than astronomy. These electronic sensors, originally designed for video telephony, became the eyes of modern telescopes, capable of detecting individual photons that have traveled billions of light years across space. A single CCD chip in a modern astronomical camera can capture images thousands of times fainter than what the human eye can perceive, effectively extending our vision across cosmic distances that would otherwise remain forever hidden. The Atacama Large Millimeter Array, constructed at an altitude of 16,000 feet in the Chilean Andes, represents perhaps the most ambitious ground-based astronomy project ever undertaken. This collection of 66 radio antennas, working together as a single telescope with a maximum baseline of 16 kilometers, can resolve details equivalent to reading a newspaper on the moon. ALMA's ability to peer through cosmic dust using millimeter and sub-millimeter wavelengths has revealed star formation happening in galaxies so distant that we see them as they existed when the universe was less than 1 billion years old. But the engineering challenges of space-based astronomy push technology to even more extreme limits. The James Webb Space Telescope required the development of entirely new materials and manufacturing techniques. Its 18 hexagonal mirror segments, made of beryllium and coated with a layer of gold only 100 atoms thick, had to be polished to a precision of 20 nanometers, less than 1/millionth the thickness of a human hair. The telescope's sun shield, consisting of 5 layers of specially designed plastic film, maintains a temperature difference of over 600 degrees Fahrenheit between its sun-facing and space-facing sides. The very act of observing the universe on cosmic scales forces us to confront fundamental limits imposed by the laws of physics themselves. The Heisenberg uncertainty principle, which governs quantum mechanical measurements, sets ultimate bounds on the precision with which we can simultaneously measure certain properties of particles. When applied to cosmological observations, these quantum limits suggest that there may be fundamental constraints on how precisely we can determine the positions and velocities of distant galaxies. The speed of light, while incredibly fast by everyday standards, becomes a limiting factor when exploring the largest scales of the universe. Even traveling at light speed, it would take over 2 million years to reach the Andromeda Galaxy, and over 13 billion years to reach the most distant galaxies we can currently observe. This means that interstellar exploration, at least using conventional physics, remains beyond our current technological capabilities and may require breakthrough discoveries in fundamental physics to become practical. Yet, the limitations imposed by light speed also provide opportunities for cosmic archaeology that no other science can match. When the Hubble Space Telescope captures an image of a distant galaxy cluster, it's literally photographing the past. The gravitational lensing effects that bend and magnify light from background galaxies allow us to study cosmic structures as they existed billions of years ago, providing direct observational evidence of how the universe has evolved over time. The concept of look-back time becomes crucial for understanding cosmic evolution. The most distant confirmed galaxy ever observed, GNZ 11, appears as it was when the universe was only 400 million years old, roughly 3% of its current age. By comparing galaxies at different look-back times, astronomers can directly observe how cosmic structures have grown and evolved throughout the history of the universe. Future missions promise to push these observational boundaries even further. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will survey hundreds of millions of galaxies to map dark matter distribution across billions of light-years. The extremely large telescope, currently under construction in Chile with a mirror 39 meters across, will be capable of directly imaging Earth-sized exoplanets orbiting nearby stars and analyzing their atmospheric compositions for signs of biological activity. The Square Kilometer Array, a radio telescope project involving multiple countries and consisting of thousands of individual antennas spread across continents, will be sensitive enough to detect radio transmissions from extraterrestrial civilizations anywhere within our local galactic neighborhood. This instrument will also map the distribution of hydrogen gas throughout the observable universe, revealing how matter flows along the cosmic web and providing new insights into the role of dark matter in cosmic structure formation. But perhaps the most profound technological breakthrough on the horizon involves gravitational wave astronomy. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will detect gravitational waves from space using laser interferometry across baselines of millions of kilometers. This space-based detector will be sensitive to gravitational waves from merging supermassive black holes throughout the observable universe, providing an entirely new window onto cosmic evolution. Gravitational waves carry information that electromagnetic radiation cannot provide. Unlike light, which can be absorbed or scattered by cosmic dust, gravitational waves travel unimpeded across the universe from their sources to our detectors. The merger of two black holes a billion light-years away creates gravitational waves that reach Earth with virtually no modification from their journey through space, providing pristine information about the most violent events in cosmic history. The detection of gravitational waves also confirms one of Einstein's most profound insights about the nature of space-time itself. These ripples in the fabric of reality demonstrate that space and time are not fixed backdrops against which cosmic events unfold, but dynamic entities that respond to the presence of matter and energy. The merger events that LIGO and Virgo detect create distortions in spacetime so subtle that they stretch and compress the Earth by amounts smaller than 1/10,000th the width of a proton. Understanding cosmic scale also requires grappling with the limitations of human perception and cognition. Our brains evolved to navigate environments on human scales, to recognize patterns in our immediate surroundings, and to make quick decisions about objects and events that directly affect our survival. The neural circuits that allow us to catch a thrown ball or navigate through a forest are poorly equipped to comprehend distances measured in light years or timescales spanning billions of years. This cognitive challenge explains why cosmic scale often feels abstract or unreal despite overwhelming observational evidence. The number 1 billion, for example, is easily written but impossible to truly visualize. If you counted one number per second without stopping, it would take you over 31 years to count to 1 billion. Yet this represents less than 1% of the number of stars in our galaxy, and our galaxy is one of hundreds of billions in the observable universe. Visualization techniques and computer simulations have become essential tools for making cosmic scale comprehensible. The Millennium Simulation, one of the largest cosmological simulations ever performed, tracked the evolution of billions of dark matter particles from the early universe to the present day. The resulting three-dimensional maps of cosmic structure formation provide intuitive understanding of how gravity shapes the universe on the largest scales. Virtual reality and augmented reality technologies offer new possibilities for experiencing cosmic scale in visceral ways. Imagine putting on VR goggles and literally flying through a galaxy cluster, watching as individual galaxies, each containing hundreds of billions of stars, pass by like distant islands in an ocean of dark matter. Or picture scaling down to molecular size and exploring the quantum realm, where virtual particles appear and disappear in the vacuum of space. These immersive technologies could revolutionize science education by allowing students to experience cosmic scale directly rather than simply reading about it in textbooks. The emotional impact of virtually standing on the surface of an exoplanet and looking up at an alien sky, or watching the collision of two galaxies unfold over billions of years compressed into minutes, could inspire a new generation of scientists and cosmic explorers. The democratization of astronomical observation through citizen science projects also provides new perspectives on cosmic scale. Projects like Galaxy Zoo have enlisted millions of volunteers to classify galaxy types in telescope images, leading to discoveries about galactic evolution that would have taken professional astronomers decades to achieve alone. The human pattern recognition abilities that evolved for terrestrial survival prove remarkably effective at identifying cosmic structures in astronomical datasets. Modern smartphone apps can turn anyone into a cosmic explorer. Augmented reality applications can overlay constellation patterns and galaxy locations onto live camera views of the night sky. Star charting apps provide real-time information about the distances, ages, and physical properties of celestial objects visible overhead. Time-lapse photography techniques accessible to amateur photographers can reveal the rotation of the Earth, the orbital motion of planets, and even the proper motion of nearby stars across multiple years of observation. But perhaps the most important technological development for understanding cosmic scale is the Internet itself, which allows instant global collaboration on astronomical observations and data analysis. When the Event Horizon Telescope captured the first image of a black hole, it required coordinating observations from radio telescopes on multiple continents, synchronizing their data using atomic clocks, and processing petabytes of information using supercomputers distributed around the world. This global collaboration represents a new model for cosmic exploration that transcends national boundaries and cultural differences. The challenges of understanding cosmic scale are so vast that they require the combined intellectual resources of our entire species. No single nation or institution can build the instruments, process the data, or develop the theoretical frameworks necessary to comprehend the full complexity of the universe. As we near the end of our cosmic journey, we must confront perhaps the most profound question that emerges from understanding true cosmic scale. What does it mean to be human in a universe this vast, ancient, and complex? The answer to this question has the power to transform not just how we see ourselves, but how we choose to live our lives and treat one another on this tiny blue dot we call home. When Carl Sagan described Earth as a pale blue dot suspended in a sunbeam, he was offering more than poetic imagery. He was providing a cosmic perspective that reveals the fundamental absurdity of human conflicts when viewed against the backdrop of infinite space. Every war ever fought, every empire that has risen and fallen, every human drama that has seemed overwhelmingly important to those who lived it, has played out on a speck of dust orbiting an ordinary star in the outer suburbs of a typical spiral galaxy. Yet, this cosmic perspective doesn't diminish human significance, it transforms it entirely. The fact that the universe has evolved conscious beings capable of contemplating their own existence represents one of the most remarkable developments in cosmic history. The neural networks in your brain that are processing these words about galaxies and black holes are among the most complex structures known to exist anywhere in the universe. The 100 billion neurons in your head, interconnected by trillions of synapses, create patterns of information processing that may be unique in our cosmic neighborhood. The elements that make up your body tell a story spanning the entire history of the universe. The hydrogen atoms and the water molecules coursing through your bloodstream formed in the first few minutes after the Big Bang, when the universe was a hot, dense plasma of elementary particles. The carbon atoms that form the backbone of your DNA were forged in the nuclear furnaces of ancient stars that lived and died billions of years before our solar system existed. The iron in your blood was created in supernova explosions so violent they briefly outshone entire galaxies. This cosmic ancestry connects you to every other living being on Earth, and potentially to life anywhere else it might exist in the universe. The same stellar nucleosynthesis processes that created the elements in your body have been operating throughout the galaxy for over 13 billion years. The building blocks of life have been scattered by stellar winds and supernova explosions across countless star systems, suggesting that the chemistry of life might be a cosmic phenomenon rather than a terrestrial accident. Recent discoveries about extremophiles, organisms that thrive in environments previously thought to be completely hostile to life, have expanded our understanding of where life might exist throughout the universe. Microorganisms have been found living in the high-radiation environment of nuclear reactors, in the crushing pressures of deep ocean trenches, in the acidic hot springs of volcanic regions, and in the permanently frozen soils of Antarctic valleys. These discoveries suggest that life might be far more adaptable and widespread than we previously imagined. The possibility that microbial life exists in the subsurface oceans of Europa, Enceladus, or other icy moons throughout our solar system means that we might not be alone even within our own cosmic neighborhood. The upcoming missions to these worlds could revolutionize our understanding of life's place in the cosmic story. If we discover that life arose independently in multiple locations within a single star system, it would strongly suggest that the universe teems with biological activity on scales we're only beginning to imagine. But understanding cosmic scale also forces us to confront the ultimate fragility of human civilization and indeed all life on Earth. Asteroid impacts, supervolcanic eruptions, gamma-ray bursts from distant stars, or the eventual death of our Sun all represent existential threats that could end human history in cosmic eye blinks. The dinosaurs dominated Earth for over 160 million years, yet they were eliminated by a single asteroid impact that lasted only seconds. Human technological civilization has existed for less than 300 years, a tiny fraction of the time that dinosaurs ruled our planet. This cosmic perspective on human fragility has inspired serious discussions about becoming a multiplanetary species. SpaceX's ambitious plans to establish permanent settlements on Mars, NASA's Artemis program to return humans to the Moon, and various proposals for generation ships capable of interstellar travel all represent attempts to ensure that human consciousness and culture can survive cosmic catastrophes that might destroy life on Earth. The challenges of interstellar exploration provide sobering insights into cosmic scale, even traveling at 10% the speed of light, a velocity far beyond our current technological capabilities. The journey to Proxima Centauri would take over 40 years. The energy requirements for accelerating even a small spacecraft to such velocities are staggering, equivalent to the entire annual energy output of human civilization. The radiation environment of interstellar space, the technical challenges of maintaining complex systems over decades-long journeys, and the psychological impacts of permanent isolation from Earth all represent barriers that may require fundamental breakthroughs in physics and technology to overcome. Yet the possibility of eventual interstellar exploration connects human destiny to the largest scales of cosmic evolution. If human civilization or its descendants eventually spread throughout the galaxy, we would become participants in the cosmic recycling of matter and information that has been operating since the universe began. Our technologies, our art, our scientific knowledge, and our philosophical insights could potentially survive the death of our Sun and contribute to the ongoing evolution of consciousness throughout the galaxy. The concept of cosmic responsibility emerges naturally from this perspective. If intelligence and consciousness are rare phenomena in the universe, as the apparent absence of detectable alien civilizations might suggest, then humanity bears a profound responsibility for preserving and developing the scientific knowledge and cultural achievements that represent billions of years of cosmic evolution becoming aware of itself. Every scientific discovery we make, every work of art we create, every moral insight we develop, adds to the universe's store of organized information and conscious understanding. The destruction of human civilization would represent not just a tragedy for our species, but a cosmic loss of knowledge and perspective that might be irreplaceable. The libraries, universities, and cultural institutions that preserve human learning become repositories of cosmic significance when viewed from this perspective. Understanding cosmic scale also provides new frameworks for addressing the global challenges facing human civilization. Climate change, nuclear proliferation, biodiversity loss, and resource depletion all appear in new light when considered from a cosmic perspective. These challenges threaten not just human welfare, but the continuation of the only known example of consciousness and scientific understanding in the observable universe. The cooperative international efforts required to address these global challenges mirror the collaborative approaches needed for cosmic exploration. The same spirit of scientific cooperation that enabled the construction of the International Space Station, the coordination of the Event Horizon Telescope observations, and the global response to the COVID-19 pandemic could provide models for addressing existential risks that threaten human survival. The psychological benefits of cosmic perspective have been documented in astronauts who have experienced the overview effect, the profound shift in awareness that comes from seeing Earth from space. These space travelers report a deep emotional understanding of the planet's fragility, the arbitrariness of national boundaries, and the fundamental interconnectedness of all human life. Many describe returning to Earth with enhanced environmental consciousness and a reduced sense of national or ethnic identity in favor of identification with humanity as a whole. Modern neuroscience is beginning to understand how cosmic perspective affects human psychology and behavior. Studies using virtual reality to simulate cosmic scale experiences show measurable changes in participants' sense of personal significance, environmental concern, and pro-social behavior. The act of contemplating vast scales of space and time appears to activate neural networks associated with awe, wonder, and transcendent experience, emotions that have been linked to increased cooperation, generosity, and ethical behavior. The educational implications of teaching cosmic scale extend far beyond astronomy and physics. Understanding our place in the universe provides context for every other field of human knowledge. History becomes the story of consciousness emerging from cosmic evolution. Literature and art become expressions of the universe becoming aware of its own beauty and complexity. Ethics and philosophy address how conscious beings should behave given their cosmic context and responsibilities. Children who grow up with a deep understanding of cosmic scale may develop fundamentally different perspectives on human nature, environmental stewardship, and international cooperation. They might view national conflicts as parochial disputes between neighboring tribes on a small planet, see environmental destruction as damage to the only known biosphere in the observable universe, and understand scientific education as preparation for humanity's role as cosmic citizens. The spiritual and philosophical implications of cosmic scale have influenced religious and philosophical traditions throughout human history. The recognition that we are made of star stuff, that our existence represents an unlikely confluence of cosmic accidents and physical laws, and that consciousness might be a rare and precious phenomenon in the universe, provides new foundations for meaning and purpose that transcend traditional cultural and religious boundaries. Rather than diminishing human significance, understanding cosmic scale reveals that significance to be more profound and mysterious than previous generations could have imagined. We are not separate from the universe, but expressions of it, temporary arrangements of stellar debris that have achieved self-awareness and begun to contemplate the cosmic story from which we emerged. In understanding the universe, we participate in the universe's own quest for self-knowledge. Now that you understand the true scale of the universe, with its countless galaxies and potentially billions of habitable worlds, you're probably wondering, where is everybody? If this cosmic silence unsettles you, check out my video called "The Universe is Empty for a Reason," and it's terrifying at the left side of the screen to discover the chilling answer that might explain why we seem so alone. It's a must-watch.